Forces assignment question. There are 5 links. Actually I count from the bottom. 1, 2, 3, 4, 5, right? There's a force pulling the 5 chains up, and the 5 chains are interlinked. The chains are going up together at 2.5 meters per second square. Now look at the diagram carefully, right? I number the chains from 1, 2, 3, 4, 5. Now, chain 1 and 2, they are in contact. So by Newton's third law, action-reaction forces, right? So the forces they act on each other will be T1. Similarly, the forces between 2 and 3 in contact will be T2, and T3 will be the force that 3 act on 4 and 4 acts on 3. Action-reaction forces here as well as here when the chains are in contact. This T4 is the force between 4 and 5, right? Now to do this question, we should consider the link one by one. We consider them from the bottom. So let me look at link 1. Draw the free body diagram. Here's a tension T1. T1 is the force now that chain 2 acts on chain 1 upwards, right? This chain 1, I label it. It has a weight of 0.1 kg. So the mass is 0.1 kg. So the weight pointing downwards from the center of gravity, 0.1 g, right? So these are the only 2 forces acting on link 1. And link 1 is going up at 2.5 meters per second square. So if you apply Newton's second law, right, I say sum of forces is equal to ma, right? Now, if you look at Newton's second law, both sides of the equation, they mean different things. This side talks about forces, so they are vectors. This side talks about acceleration, okay, which has a direction as well, but this is the resultant acceleration of the object, right? So both sides are different. Now, when I look at the left-hand side, I would like to sum all the forces that's acting on link 1, which is then T1 minus 0.1. Why? Because the summation of forces, the resultant direction, must be the direction of the acceleration. Since my acceleration is pointing up, right, it cannot be 0.1 g minus T1. Rather, it must be T1 minus 0.1 g, because the resultant force is pointing in the direction of acceleration, which is pointing upwards, right? So the right-hand side of my equation will be 0.1, which is the mass of the link, multiplied by 2.5, the acceleration, right? You shift this term over to the other side, you get this, okay? And you sum them up, you should get the answer 1.23 Newton. Okay, now if we do link 2, we can draw the free body diagram of link 2. Link 2 should look like this, right? Should look like this. It's going up at 2.5 meter per second square, right? This is link 2. Okay, now yes, T1 pulling it downwards, right? This is link 2, right? Link 1 is applying a force on link 2, T1 downwards, and link 3 is applying a force T2, right, pulling it upwards. And it also has a mg, yes, its own weight downwards, right? So when I apply Newton's second law again, I should be looking at this, right? Now the resultant force then would be T2 minus T1 minus mg is equal to 0.1, 2.5, right? Now I already calculated T1 to be 1.23, right? So I move T1 and mg to the other side. I should be getting T2 is equal to 0.1, 2.5 plus 1.23, right? Plus 0.1 g, okay, 9.81, right? That should give me 2.46 Newton. Okay. Then the rest is pretty similar. You see, if you look at these two free body diagram, right? This has a tension 1, a weight, but there's no tension below because this is the last link. Every other link, link 2, link 3, and link 4, is very similar. In fact, even link 5 is very similar. it has a tension above, a tension below, and its own weight as well, right? So if we were to do a similar, repeat similarly for link 3, 4, and 5, it actually follows the pattern of link 2 in terms of the free body diagram and the equation, right? So let's link 3, right? So you should have mg, T2, T3, right? And it's going up at 2.5 meter per second square. So when I do Newton's second law, right, I should get T3 minus T2 minus mg equal to 0.1, 2.5. So T3 is equal to 0.1, 2.5 plus T2, which is 2.46, right, plus 0.1, 9.81. It should give you 3.70 Newton. Okay. And if we were to do this for link 4, then you have T3, T4, mg, right? Again, it goes up at 2.5 meter per second square. If I apply Newton's second law to this, I should get T4 minus T3 minus mg is equal to 0.1, 2.5. T4 is equal to 0.1, 2.5 plus T3. T3 is 3.70, right? Plus 0.1, 9.81, right? And that should give you 4.93 Newton. Okay, then let's look at that is actually the first part, right? Part A. Now if you look at part B, it is very similar. Part B is basically applying this free body diagram on link 1, on link 5, sorry, right? Okay, link 5 over here. Okay, let's go take a look. So this link 5, right? So it's a T4, there's a mg, right? And this F, correct? It's going up at 2.5 meter per second square, right? So if I apply Newton's second law to this, I get F minus T4 minus mg is equal to 0.1, 2.5, right? It's the same, and if you do that, you actually get F is equal to 6.16 Newton. Okay, now the last part C is simple if you understand. It says the net force acting on each link, right? Okay, the net force acting on each link, right, must be equal to MA, right? Basically that's it. And since every link has the same mass, 0.1, and they have the same acceleration of 2.5, right? They have the same net force, right? So although the tensions for each tension experienced by the links are different from T1 to T4 and even F, they are different, right? The net force experienced on each link is given by MA, and since each link has the same M and same A, they have the same net force acting on them, 0.25 Newton, and that's it.